Hello students. So today we shall continue with this lecture, that is modeling for analysis. In the previous lecture we had seen about the approximate analysis for the plane frames and the plane shear walls. So now next we shall see is the three-dimensional frame and the wall structures. Now in this, the high-rise rigid frame structure, that is a rigid frame structure, has the moment resisting joints, and the columns and the beams, they will be modeled as 3D beam elements. So I'll just show you in the previous lecture the beam elements we had seen. So this is the beam element, quadrilateral membrane element, the truss element, and the quadrilateral plate bending element. So here there will be three translations and the three rotations at one end for the beam, at the other end three translations, three rotations, total 6 degree of freedoms. Here 2 degree of freedoms at each one, at each node you can say. Here it will be a single axial, and for this quadrilateral plate there will be two rotations and one translation here. So these are the degree of freedom. So here first for three-dimensional frame and the wall structure, the beams and the columns, they will be modeled as three-dimensional beam elements. So this is the beam element. Now here you can see in the figure, this first figure you can see. So here all these beams and the columns of this rigid frame will be taken as beam elements. Okay, so it is shown as three-dimensional beam elements. Now here they will deform axially in shear and bending in two transverse directions, and twist also will be there. That is a rotation. Twist will also be there, and so they will be they have to be assigned an axial area, two shear areas, and two flexural inertias and a torsion constant. Since it is a twist, you have to give the torsion constant. So these are the assignment or the assigning the values, that is assign an axial area, two shear areas, and two flexural inertias and a torsion constant. Then the shear deformations of the columns and the beams, okay, and also the axial deformations of the beams, they are very small, and hence they will be allowed for the omitting, okay, the assignment of shear area by using a large axial area. Okay, so since the shear deformations of the columns, beams, and the axial deformations of the beams are very small, they are allowed for by omitting the assignment of shear area and assigning it as a large axial area. Then the torsional stiffness. Okay, since the twist is present, so the torsional stiffness of the beams and the columns will be neglected. Okay, which will be allowed for by omitting the assignment of the torsion constant. Okay, the next, hence the results of the translations and the rotations of the nodes. Okay, so whatever results of the translations and the rotations of these nodes will be there. Shear forces, bending moments, and axial force in the column, shear force and the moments in the beams will be obtained here. Okay, so your shear force, bending moment, axial force in the columns, shear force and moments in the beams will be got here. Then the three-dimensional shear wall. Okay, this was the plane here. So three-dimensional shear wall are the major lateral load resisting components. Okay, the shear wall, they are the major lateral load resisting components for the high-rise structure, and which occur in multi-branch, that is multi-branch. It may be in the open section shapes, it may be a closed one, or it may be a beam connected section. So I'll show you in the figure here, the second figure. So this open section shear wall. So this is open here, this section shear wall, or it may be a closed shear wall, that is partially closed, openings are provided, partially closed shear wall assembly, or it may be a non-planar wall connected by beams. Okay, this is the non-planar wall connected by beams. So here it is as shown in the figure. So the shear wall, they will be the major, they will be the lateral load resisting components. The closed or the open forms, the principal actions of the walls will be in the plane shear and flexure, and the interaction between the walls of an assembly is vertical shear along the joints. Then next, now the plane stress membrane elements. Okay, now plane stress membrane elements, they are highly suitable for modeling the 3D shear wall components. Okay, you can see here the plane stress membrane elements. The membrane elements can be used, okay, to represent the shear walls. So it is plane stress membrane elements. They are suitable for modeling the 3D shear wall components, and story height, wall width elements, they give the accurate or the correct representation, since the representation will be correct here. Then the plane stress elements, they are not suitable for the wall systems. Okay, the plane stress elements, when we define it, they are not suitable for the wall elements as they will lack the transverse stiffness. The transverse stiffness provided provision at the orthogonal wall connection. So suppose at this orthogonal wall connection, this transverse stiffness, they will lack there, and they will allow for the stiffness matrix analysis of the problem. So when using alone the plane stress membrane elements, they provide the out of plane rigidity, okay, to maintain the shape of the core in a in particular shape. So in reality, by in plane rigidity of the floor slab. So what happens due to that orthogonal wall connection, the lack of transverse stiffness, so the wall connection will allow us to stiffness matrix analysis of the problem will be there. And to overcome this remedy, what they do is they add at each nodal level, that is at the each floor level or at each nodes, a horizontal frame of fixtures, that is imaginary type, rigid auxiliary beam will be provided. Here you can see this is a beam. So horizontal rigid, this dotted one, horizontal rigid frame of auxiliary beam. So here we provide is the auxiliary fixtures, auxiliary rigid beams will be provided. You can see here. And these are the plane stress elements. 1, 2, 3, these are the plane stress elements. And the dotted one which is shown above is the horizontal rigid frame of auxiliary beam. Same way here also. The dotted here is horizontal rigid auxiliary beams. Okay, and here at this ends, at the joints and corners, you can see is the horizontal. This at this point at here, especially in this figure, you can see there is an auxiliary torsion column. Okay, and these are the plane stress elements. And this part is the real connecting beams, which is assigned to be rigid. Okay, 1, 2 here, and these dotteds on top of this here mentioned, they are horizontally as well as vertically rigid auxiliary beams. Okay, so this is for membrane element and auxiliary beam model. Okay, so this is for membrane element. So here you can see beam element, membrane element. So now further what they have told is we represent it by a rigid auxiliary beam. So if walls are connected in plane to each other or other parts by beam, the auxiliary beam which is adjacent to the wall edges can be represented or can be made vertically rigid so as to cause the transfer of moment. So here you can see the vertically rigid is also provided. These are only horizontally rigid auxiliary beams, whereas at the edges here, to transfer the moment, it is horizontally and vertically rigid auxiliary beams. So it is mentioned if the walls are connected in plane to each other or other parts by beams, then they will be vertically rigid also to cause the transfer of the moment. Now suppose, now as I said, these were the membrane. Suppose if shell elements are used for model, but not in case of plane stress elements, the torsional stiffness to twisting of the walls is to be accounted. Okay, so it is therefore introduced by adding to the model a fixtures column, that is as I shown there. The torsion constant also will be provided. In this you can see at this edges here a auxiliary torsion column will be provided. Whereas this torsion column or the constant will have a value which will be equal to sum of individual walls of the torsion constant. The summation of the individual walls torsion constant. And the axial area and the inertia of the column will be 0. Okay. Then to represent the beams which are connecting these shear walls in the same plane is by story height membrane element with vertical shearing stiffness which will be equal to vertical displacement stiffness of the beam. So here the beam connected wall assemblies membrane elements representing the beams. So here membrane elements are representing the walls and here membrane elements connecting the beams. So this is the other type. That is when we represent beams which are connecting the shear walls, same plane, story height membrane elements with vertical shearing stiffness. That is vertical shearing, whatever the stiffness, should be equal to vertical displacement stiffness of the beam. And in such models, the auxiliary beams which are provided, they are required to form horizontal rigid frames around each level of the wall assembly. So here they need to form the horizontal rigid frame around each wall assembly. But the beams which are adjacent to the openings, they do not have the vertical rigidity or vertical rigid. Now these were the study of the approaches or the techniques for the accurate analysis, the approximate analysis. Okay. Now this is, as I said, it will be the analysis, the modeling which is to be done of the structure in the analysis. So these are the different approaches and how is to be defined when doing the analysis part. Now next we shall see is the reduction techniques. Reduction techniques is what are the different techniques where we can reduce the work of the analysis part, okay, or the modeling, whatever model we do, since it will be a large and complex one and it will be difficult for computation. So we need to do a simplified model so that if it is a very complex one, what happens, it becomes difficult for keeping all the bookkeeping and all the computation. So therefore we prefer is a simplified model which will provide the accuracy as same as the accurate one as a detailed model. So the following techniques are used to simplify the model. So some of the techniques that whichever we will be studying here, they do not that is diminish or they do not reduce the approximately or the accuracy of the analysis, while some of them they lose a little amount of accuracy as compared to a final design analysis. So some techniques which we use which will give the as accurate analysis or accurate result as the model is, as well as some they will give a slight variation in the results. So the reductions are therefore applicable to both detailed and to a simplified models of analysis. Okay, so you have the reductions, they are for detailed and the simplified model when we go for the analysis. So in this we will be seeing the different reduction techniques will be first one symmetry and anti-symmetry. Next is two-dimensional models of non-twisting structures. Then two-dimensional models of structures that translate and twist. Then we will be studying about the lumping, and last one is the wide column and the deep beam analogies. So these are the different techniques which we can use to get a simplified model. Okay? Since the detailed model will be complex, so we make it a simple version for the analysis. Whereas here, it doesn't mean that the same, it means that whatever we have defined in the previous one, that remains the same. But only for the modeling when we are going, the reduction techniques we can use any of these. Okay, so first one we shall see symmetry and the anti-symmetry. So we know symmetry is as it will be having the same plans here. So a structure which is symmetry in plan about the axis of horizontal loading. So here in the first figure you can see this arrows what are showing they are the horizontal loading. So here as per the axis of symmetry for the structure and the loading, it is symmetrical. So on the either side you can see it is symmetry, it is the same one. So here, a structure which is symmetry in the plan about the axis of the horizontal loading. So it is around the axis of horizontal loading. As the load is acting here, this is the axis. So this can be analyzed as half of the structure. Okay, when you cut it in half of the structure as shown here. Okay, it can be analyzed half of the structure to one side of the line of symmetry subjected to half of the loads. So if you cut the section and you consider this half part of the section wherein the half loads are acting. So this way we can do the analysis here. So the ends of the members, so whatever we cut here, these ends of the members cut by the line of symmetry, they are considered, or they are constrained, or they are not allowed against the rotations, okay, horizontal displacement in the plane perpendicular to the direction of loading, okay, or displacement in the perpendicular direction of loading, and then against rotation about vertical axis, okay. So it is constrained about constrained against rotation, horizontal displacement in perpendicular to the direction of loading, and against the rotation about the vertical axis, whereas it will be free to displace vertically, okay, it can displace vertically, and it will be allowed to translate in the direction of the loading. So this is the direction of loading, so it is allowed to translate in the direction of loading. So here you can see the edges which are cut here, as mentioned, it is restrained against the translation in the y rotation, that is the vertical rotation, it is constrained here. Then the results which are obtained for these, that is the deflection and the forces, they will apply symmetrically to the corresponding nodes and the members in the other half of the structure. So whatever results you get, the deflections, the forces, the same values will be obtained for the other side or the other half of the structure. Now this is when it is in the, that is we can see that this is the loading and this is the axis of symmetry. Next is when a structure which is symmetrical in plan, okay, this is a symmetrical structure in plan about the horizontal axis perpendicular to the axis of the horizontal loading. So this is the horizontal loading and this is the perpendicular axis of symmetry. So this is the anti-symmetrical. So this is called as the axis of anti-symmetrical behavior, since the horizontal loading is perpendicular to it. Then in this case what we do is, again it is cut into half of the structure to one side of the axis of symmetry, and here it will be subjected to the half loads, or the loads of half values need to be analyzed. So this is to be analyzed here. Then these cut members, that is the end of the cut members, they will be constrained against the vertical displacements, okay, but here they will be free to rotate in the vertical plane. They will be free to rotate in the vertical plane and parallel to the direction of the loading. So this parallel to the direction of loading, the rotation will be allowed here. And the results for the half structure which is to be analyzed apply to the other half of the structure. Now suppose if the structure is double symmetric on plan, it is double symmetric, there is two symmetries is considered and subjected to horizontal loading along one of its axis of symmetry, it can be analyzed by considering 1/4 of the structure. Okay, here we consider half, there we can consider 1/4 of the structure with proper constraints at the ends. Okay, so at the ends, whatever where you cut, the proper constraints are to be applied along the line of symmetry to represent symmetrical and the anti-symmetrical aspects of behavior. So this is the first one, symmetry and the anti-symmetry. Next reduction technique we shall see is the two-dimensional models of non-twisting structures. Now in this, the assumptions, as we have seen in the previous one, we assume that the floor slabs are rigid in plane, so which will permit the horizontal displacement of the vertical elements at each floor level, and then they can be defined in terms of slabs horizontal translation and the rotation. So it will be having the horizontal translations and rotation, and here we can represent the 3D structure to 2D structure, 2D model. So because of this assumption where we consider slab as rigid one, which will allow the horizontal displacement of the vertical elements, that is the columns. So here what happens, the slab will be having the horizontal translation and rotation, so which will allow for the representation of 3D structure to a 2D model. So now here it can be explained when we consider this technique for planar representation of non-twisting structures and then extending it to twisting structure. So now here it is given as non-twisting. So first what we do is we apply the technique for the planar sections for the non-twisting, and then we extend it for the twisting structures. So now when the structure is symmetrical in plan and loading and they do not twist, that is a rotation, the twist is not allowed. So which means that the displacement, that is the horizontal displacement of the vertical elements will be same at each level. So that is at each floor level, the horizontal displacements of the vertical elements will be same. Then for symmetric structural analysis of half structure is done. Same way we go for the half structure, and the identity of displacement at floor levels is shown by a planar model. So it is shown by the planar model, which will be representing planar model by assembling the bends in the same plane or in any order of spacing and providing the horizontal constraint. So here in this figure you can see here, now here symmetric structure with parallel bends, okay, and here is the equivalent two-dimensional structure. So now in this first A figure, as they have given, it is with parallel bends A to B, okay. So here is the rigid frame, the shear wall, then C to D, E, F, then this is the axis of symmetry where it is cut, then same way it is applied on the other side. So since it is same, so axis of symmetry is cut here, and this is the load acting. Now when you transfer this to a 2D model, how it is represented is shown here. That is only the half structure. This part is not there. Only this part is shown, which is here in the B figure. So how it is shown is, this is the loading. This is A to B. So this A to B. First is what here is the rigid frame. So this rigid is shown here. And then this is the shear wall. So this is the shear wall shown. Same way A to B. Now when you represent C to D, C to D, okay, C to D is, first you have is a plain wall, then you have this rigid frame type, and then again you have a plain wall. Now interlinking between the B and the C, between this B and C, they have the rigid links, okay, that is we call it axially rigid links will be provided. Now next is E to F. E to F, first we have is this links will be there, then again we have the same again these rigid frame. Now connection between D to E is again with the axially rigid links. So this is how we give the two-dimensional model. Okay, so that is what is explained in this here. That is, for symmetry we cut it into half the structure is done, and the identity of displacements at the floor levels is shown by planar model. That is, the planar model is shown here by assembling the bends in the same plane in any order. So as I have shown, A, B, C, D the spacing, and the bends are shown, and they will be that is the horizontal constraint between the bends at each level will be provided. So if the analysis program, that is when you do computer analysis, it has a dependent node option. That is, if you have a dependent node option given there, then the set of the nodes each bend at the same level will be assigned the same horizontal displacements. It will be having the same horizontal displacement at each level. Suppose if that dependent the node option is not there, then we go for this axially rigid pin ended links. Okay, that is, if this option is not there, then the pair of the nodes which are there at the same level in the adjacent bends, they will be joined by the axially rigid links there. Okay, then the shear in the slabs between the bends can be found by considering the difference between the shear in the successive stories of each bend. So whatever shear slab will be there, that value we can find by the difference between the shear in the different stories or the successive stories. Then the axial forces in the beams and the links of the models, they are not correct, as the loading and the horizontal, that is the value what you get the axial forces in the beam, they are not correct. This is because in the actual they do not represent this plane location in the real structure. Okay, that is, in the real structure this representation is not correct. So due to that, the axial forces in the beams of the link models, you do not get the correct values. This is of this figure which is explained. Then if the structure is having the connected orthogonal bends. It is a symmetrical structure and it is with orthogonal bends. So that time what it shows is, I'll show the figure here. So orthogonal bends, that is you'll be having the joints at the surfaces. That is example I can show you. Suppose this is there, this is a wall, and this is the wall and this connecting. So you can say that the wall and the connecting beam. So orthogonal bends you can say. So now suppose the structure is with orthogonal system of connected bends. They will be symmetrically located about the axis of horizontal loading and they can be modeled for analysis by the extension of planar. So same planar modeling technique is to be applied. Here also in half plane, that is along the axis of symmetry, it will be cut. So the half planar model will be there and half the parallel bends. So here the parallel bends and the perpendicular bends, they will be grouped separately here in this case. Okay, since the axis of symmetry is there, so it is orthogonal to be along all sides. So here parallel bends, perpendicular bends, they will be assembled or made into separate groups, and each bend, in each bend, the column will be assigned the inertia to its bending in the plane, and the nodes in the model will be numbered. So whatever nodes are there, these nodes, they all will be numbered in case of the orthogonal bends. Then the horizontal displacements of the parallel bends, they are established by using the dependent node option or by again auxiliary rigid links. That is as shown here. If the dependent node option is there, you can go for it. If it is not there, then the auxiliary rigid links will be provided. Then the vertical displacements between the parallel and the perpendicular bends. Okay, the group which is made separate, the vertical displacements of this, they can be found out either by constraining the nodes that are the same in the parallel and the perpendicular to have the same vertical displacement. That is, they both should have the same vertical displacement, or else to dimension the model horizontally. Okay, you can make the model horizontally so that vertical connecting links, that is on the frames, they are coincident with the parallel frames. That is, perpendicular frames, they are coincident with the parallel frames. The next is two-dimensional models of the structure that translate and twist. So in the previous one it was two-dimensional models of non-twisting, whereas next is you will be seeing here is the two-dimensional model which will translate as well as twist. So this is the third reduction technique. Now in this, the same way, the assumption that we make is the floor slabs, they will be rigid in the planes, and it will imply that an origin and pair of axes which is parallel to the orthogonally oriented beds of laterally loaded structure, resulting displaced location of the floor slab, and they can be defined by rotation of the slab about the origin and two displacement parallels to axis. So now here, this is suppose the structure A, B, C, D. This is the initial position. Now since here it is allowed to translate as well as twist, we can see the first position is here. This is the initial. Then it moves to second position where the rotation is about the arbitrary origin here. The third displaced in y direction and then it is displaced in x direction. So here the angle will be provided. It is moved to this position here. Okay, dotted, first dotted you can see here. Then wherein the angle is provided. So rotation is there, twist is there. Then when it moves to the next position, okay, the y displacement is there. And then here in the final position you can see there is a displacement in the x direction. So 2 and 3. Okay. So here in this case you will be having the rotation as well as the displacement in the x and the y. That is given here. Two displacements parallel to the axis and rotation of the slab about the origin. This takes place when the structure is allowed to translate and twist here. So the horizontal equilibrium of any slab, that is the external x and the y directions on the slabs, and the combined movement about the vertical axis through this origin, it must be in equilibrium with the capital X and this capital Y directions, resultants of the reactions from the bends and the and their resultant moments about the origin. So they should be in equilibrium. Okay, whatever axis the displacements are there, horizontal equilibriums, it should satisfy. Then the structure with planned asymmetric system of orthogonal bends that are stiff in their planes but have zero transverse and torsional stiffness. They have the zero transverse and torsional stiffness. A two-dimensional model can be formed to satisfy the condition of displacement and equilibrium. So when it is plan is there and it is asymmetric system and it has zero transverse and torsional stiffness, we can go for 2D model to satisfy this displacement and equilibrium. The next is a 2D, that is a two-dimensional stiffness method of analysis for the planar models. When it is subjected to transformed loads, they will give the results for deflection and the member forces as same as that of the 3D analysis. And provided that the analysis assumes that the plane is in plane rigidity and it has zero transverse and the torsional stiffness. So it should have the zero transverse and torsional. Then the results of 2D will be same as that for the 3D analysis. Then if the structure has the core, okay, that is core, inside core is there, and it is with shear walls, then it can be treated as individual wall as a bend, and it will represent a stack of plane stress finite elements. We can represent it as a plane stress finite element, and we assign the nodes, rigid arms, and whatever constraints are there as per the bed. That is as it was another bed. That is another model of it. So we have to represent it with nodes, rigid arms, and constraints. That is, if the structure is having the shear walls on the core. Then the flexural stiffness, which is assigned to these connecting arms, that is as we have seen auxiliary rigid arms, connecting arms, it is recommended to assign an inertia such that the arms, whatever arms are considered as vertical cantilever fixed at governing node, and the lateral stiffness at the lower end will be greater than the estimated stiffness at the level where the arm connects. So whatever the rigid arms which are there, they should be assigned the flexural stiffness, the inertias, such that, okay, the whatever arms they are provided, they are considered as vertical cantilevers. They will be considered as vertical cantilever which are fixed at the governing node, and the lateral stiffness at the lower end will be greater than that stiffness which is estimated when where the arm is connected. The next technique is lumping. The next technique, the reduction technique, is lumping, which means the combination of several of a structure's similar and similarly behaving components or the different assemblies, which we combine it into a single equivalent component. Okay, what it means is it is a combination of structures similar and similarly behaving components. The different components which are there, the beams, columns, if they have the similar behavior, then we can represent it into a single component, okay, or assembly, in order to reduce the size of the model for analysis. So this we do is for reduce the size of the model for the analysis. So whatever resulting forces we get in the equivalent components of the assembly, they are subsequently distributed to give the forces in the original units. Whatever forces and the values we get from that lumping model, that will be distributed to the original units in the subsequent manner. So now lumping. First is lateral lumping. In this you have the lateral and the vertical lumping. So in the lateral lumping, what we do is the symmetrical and the symmetrically loaded structure, which consists of two identical shear walls and three identical rigid frames. Now in this figure, you can see these are the two shear walls, black one, and these are the 3, 1, 2, 3. These are the identical rigid frames. Now the walls, they can be lumped laterally into single wall. Okay, so whatever the shear walls are there, they can be lumped into a single wall, which will be having twice the inertia of the individual wall. So now this wall which is there, you show it as a lumped wall having inertia which is twice that of the individual wall. And these frames 1, 2, 3, these also can be lumped into a single frame, but wherein the property will be having 3 times that of the individual frame. Okay, so whatever frame value is there, it will be 3 times that. So now here you can see this is one equivalent wall. Okay, the shear wall which is there, this is represented as one equivalent shear wall which is having the inertia 2 times as that of a single individual wall, whereas this, that is 1 2 3. Okay, that is, first you can see first one is a dotted one, so this is the rigid frame, then second rigid frame, so this is similar, 1 2 3, they are similar, so it can be represented as a single one here, but whatever values are there, that will be equivalent to 3 times, because it is 3 equivalent we have considered, so 3 times we will be getting, and they are connected again by the auxiliary rigid arms. So it is assembled as a planar model. This is a planar model here, and whatever forces you get in the wall and the frame of the lumped structure, they will be divided by 2 and 3 respectively. That is, if you want for the wall, it will be divided by 2, the results, and if you want of the frames, it will be divided by 3, whatever results you get. So it is applied to the structures which do not twist. Okay, this condition is for not non-twisting, because the forces which will be there in the bends of the non-twisting structure dependent of the lateral location. So whatever lateral twisting, if it occurs, it depends on the lateral location. So this is not suitable for the twisting structures. This is the lateral lumping here. Next we have is vertical lumping. So now in vertical lumping, what happens is, in the tall multi-storied coupled wall, I'll show you the figure here. This is the vertical lumping here. Okay, these two figures here, vertical lumping. So now in the tall multi-storied coupled wall or the rigid frame structures, that is, if you have the coupled wall structures or if it is a rigid frame structure wherein the repetitive story height and the beam size are there, then the detailed model, it can be simplified, okay, by lumping it vertically, or we say it as combining the groups of 3 or 5 beams into a single beam. So here what we do is, the beams which are similar throughout the height, what we can do is, we can combine the groups of 3 or 5 beams into a single beam at the middle beam location and assign the lumped properties for, that is, of inertia and the shear areas. So now here it is shown here. This is the wall which is there, coupled wall with respective beams. Okay, now this is shown here. These are the coupled walls and these are the beams here. Now this representation is equivalent lumped beam model. This is lumped beam model. So what is done is, these beams which are there, they will be coupled into one here. They will be lumped into one model. So at the top and at the bottom you keep it as the same, whereas in between we lump it vertically. So 3 beams, they are clubbed into one, so 3 LB. Again 3 beams, they are that is lumped into one vertically. They will be represented here. So that is shown here, lumped beams, 1 2 3 here. So these 3 beams means 1 2 3, 3 beams together, they are shown here. Again next 3 beams which are same, again it is shown here, right? So these are the walls which are represented by membrane element. The walls which are there at both sides, will be represented as membrane element. These are the lumped beams here. So now in this, 1 or 2 beams at the top and the bottom, they will be kept at the original location. As I said, at the top and the bottom will be kept at the original locations there, so that to represent the localized effect at the top and the base. Then in shear walls which connect the lumping beams, the sectional properties of the membrane element or the wide columns representing the wall should be same in the lumped model or in the non-lumped model. This is because of the single curvature behavior of the wall. So in shear walls which are connecting these lumping beams, the sectional properties of the membrane element or the columns which are representing the wall, they should be same as that of the lumped model as in the non-lumped model. That is, these sectional properties, they should be same in the lumped as well as in the non-lumped model. Okay. Then if coupled walls are represented by membrane finite element, in rigid frames, the story height, the double curvature bending of the columns requires inertia that is to be increased in lumped model. So now here in this, when we consider the membrane element, the inertia is to be increased. Okay, in the lumped model here, This is a membrane element here we represent. Since it is a beam, lumped beam we have done, here membrane element we represent. So here it is mentioned beams represented by membrane element and the walls are represented by membrane element. So in this case what we do is the double curvature bending will take place. So for that we need to increase the inertia in the lumped model. So okay, with increase in the story height, so that to make it is lateral stiffness in both the models. So axial areas are also to be same in both the models. Then if the coupled walls, they are represented by membrane finite element. Okay. Then the lumping technique varies with the sets of n successive connecting beams. So the different number of connecting beams as well as the shear walls by n story height. That is as n number of story height membrane elements. So now here it is shown. This is the rigid frame with repetitive beam and here is the equivalent lumped beam model. Okay. And this is the membrane element, representation by membrane element. Now this is for membrane element, this is for the beam element. So here the inertia is to be increased. Okay, in this model, the inertia is to be increased as we are representing in beam model. When we go for the membrane element as the n number of stories, where it is shown here, coupled walls represented by membrane finite element. The lumping technique is having n successive connecting beams as well as shear walls by n story height membrane element. So it will be represented how many membrane elements are there as per the height of the structure. So we represented according to the number there. Then the resulting moments and the shear which is there in the original middle beam of the lumped sets of the n beams are 1n of the values of the lumped beam. So whatever you get the results of the moments and the shear in the original middle beam, in the middle beam of the lumped set, it will be having 1 by n, that is 1/n of the resulting values of the lumped beam. Okay, and the forces in the other beams are valued by interpolation. So whatever other forces you want in the other beams, their values are to be found out by interpolation. In this case it is equivalent membrane. Okay, when we go for membrane element, when we go for beam element, and this is also the beam element representation. So all these techniques, they are to be applied when we go for reduction techniques in the analysis of the models. So this will complete about the module 4 about the analysis, that is modeling for analysis. Thank you.